Next presenter is Dan Popok. As a professional engineer, Dan has a 36-year history developing thermal modeling software and using those tools to solve challenging thermal problems. He received his bachelor's and master's degrees at North Carolina State University in 1982 and 1983, beginning his love affair with thermal sciences and numerical methods, and has remained engaged in these subjects ever since. He discovered his bioanalytical tendencies while working military and NASA thermal and structural projects at Harris and Teledyne Brown, and in 1996 transitioned to independent contracting. He soon became the principal developer of Cinda/G for his main consulting client, Network Analysis. There he developed new features, solvers, and translators integrating Cinda/G with finite element modelers for graphical preprocessing, while supporting users and working a wide variety of aerospace and commercial consulting gigs. MSC Software captured him as a direct employee when they acquired Network Analysis in 2008. He continued as a lead Cinda developer, but wore other hats, including engineering services, marketing, and user support. Deciding he no longer wanted to be a software developer when he grows up, Dan left MSC in 2019, returning to the engineering lifestyle by joining the Jacobs team via Link Research, supporting Marshall Space Flight Center as a subject matter expert. Go ahead whenever you're ready, Dan. Dan, we cannot hear you if you're talking.
Nick, can you unmute him?
Testing, can anybody hear me?
Yes, we can hear you now.
Okay, I was looking for the unmute button and seemed to have lost it. Sorry about that.
No worries, we got you. Go ahead.
All right, I'm going to begin. Okay, the air-safe pump in 4-bed is part of the adsorbent bed regeneration cycle. It removes air from the bed and sends it back to the cabin. It's a commercial off-the-shelf scroll pump compressor unit. Kind of sounds like a large aquarium pump. And it's repackaged in an acoustic enclosure to reduce noise, and that leads to a thermal challenge. By mounting this thing on a cold plate and putting it in the enclosure, we have competing thermal goals. We have to keep the pump and its motor cool enough while simultaneously not getting so cool that we start forming condensation. Testing with the flight unit showed strong potential for condensation with surfaces below 60 degrees Fahrenheit. We developed a test-calibrated model and used that model to investigate design changes to find a balance between those thermal goals, and did find it. And then finally, we did a condensation analysis to predict how much condensation could be formed by the pump under worst-case cold conditions. So, as an outline, I'm going to show what the 4-bed system is and how it works very briefly, and describe the off-the-shelf air pump, then the characterization testing that showed the condensation risk. Then I'll talk about the correlated model and the condensation eliminating design modifications. Then I'll talk about how we tried to predict or quantify the condensation formation. All right, so CO2, it's a CO2 scrubber for express rack. It consists of 4 beds. There's 2 beds that absorb CO2 and 2 desiccant beds. There's 4 fluid interfaces, so it's fairly complex. We have avionics air that cools through the rack. We have low temperature loop cooling, which runs from 38 to 50 Fahrenheit, which is pretty cool. There's process air, that's the air from the cabin that gets the CO2 extracted and then sent back to the cabin. And there's a vacuum port that's used to dispose of the CO2 that's extracted. The low temperature loop cools the process air before it gets to the absorbent bed. The CO2 absorbent beads work a lot better on cool, dry air. And then after doing that, the water flows through the cold plate to cool the air-safe pump. On the left and the right here, we see some pictures of the hardware and the process of assembly. That process is ongoing. The left is a little earlier in the process. On the right, we have some baffles that have been put in front of it. The desiccant beds are on the bottom. The absorbing beds are on the top. These cylindrical soup cans are air selector valves that switch the flow between the two half cycles, which I'll talk about momentarily. In this CAD image, we can see this is where the air-safe pump is compared to the front panel. Here's other avionics. Here's the beds. And here's the fans that bring air in from the avionics air cooling system. In this view, we can see how the LTL flow path traces through the system. It runs through this pre-cooler, which pre-cools the process air, runs back around, comes down, cools the air-safe pump. So this is the guy we're working on. The model we did for this will be integrated into a system-wide model that's still being developed. So the 4-bed CO2 scrubber operates in two 80-minute half cycles. During each half cycle, one absorbing bed is scrubbing CO2 while the other regenerates. One desiccant bed is drying the incoming cabin air before it goes to the CO2 absorber. The other desiccant bed is rehumidifying the air before it gets back to the cabin. So the two beds are kind of flip-flopping between these states. The air-safe pump participates in the absorbent bed regeneration process. So during the 80-minute half cycle, for the first 10 minutes, it's pumping residual air out of the absorbing beads to return it to the cabin. And once it's in a near vacuum condition, it's opened up to a vacuum line. Heaters are turned on to drive the CO2 out of the beds, and the CO2 is thrown overboard. These two images illustrate the two half cycles in comparison to each other. You can see how the desiccant beds flip-flop between the half cycles, and you can see how the absorbing beds flip-flop through the half cycles. The next 25 slides, I'm going to go through them at about 1 or 2 seconds apiece. It kind of provides a pseudo animation to show how the cycles work. So I'm just going to flip through them pretty quickly. Okay, this is an introduction to the off-the-shelf pump. This is what it looks like from the manufacturer. It's on a little carrying plate and it has a fan cooling system. There's a motor control board that's integrated with the pump. We take it off this plate, we get rid of this fan, and this board is moved, the function of this board is moved into an avionics box. The pump is rated to operate in this configuration in a 50C ambient rating. The pump case can get up to 70C. The motor case can get up to 65C. The motor is about 75% efficient. The pump is about 4% efficient because it's working against vacuum most of the time. In its repackaged form, it looks like this. Some insulation is not shown in the diagram, showing it with and without the cover. The pump and the motor are here. There's a cradle underneath it that mounts it through these aluminum standoffs to the cold plate. Secondary cooling path comes up through this cold block to these thermal straps and then down through these pillars to the cold plate. For humidity assessment, we're using the humidity temperature envelope from SSP 57000. We're extrapolating this red box over to about 30 degrees C to apply inside the rack. We don't really have any inside the rack temperature humidity envelope, so we use the cabin condition. Typically, you don't ever have any more than a 75% humidity or a 60-degree dew point. So that's why 60 degrees is kind of a critical temperature. Anything getting below 60 degrees has to be looked at in terms of a condensation threat. During testing with the flight unit, this is a summary, everything on one graph. These temperatures are for the controller. The rest of the temperatures are for various locations on the pump illustrated here. The main point on this graph is that we have a lot of temperatures that are below 60 Fahrenheit. So this all is a possibility for condensation and has to be addressed. So this creates a thermal conundrum. If the pump had been flown in its commercial configuration, we could have just made sure that the air around it is below 50 C. And since the rack air is less than 100% relative humidity, and the pump's always warmer than the rack air, there would never be any condensation. But because we put a cover on it, stuck it on a cold plate, we have to consider the condensation. And it creates the competing thermal demands of keeping the pump cool enough, not getting so cool that we start making moisture, liquid water. The LTL temperature ranges from 38 to 50 Fahrenheit. The pre-cooler can warm that water by as much as 10 Fahrenheit, but that's not a hard number. Don't know how much confidence to put in it. We had a lot of difficulty with the testing of the pre-cooler heat exchanger. So in the analysis, we made a thermal desktop model of the air-safe pump, which will later be integrated into the system model. This model was dialed in to agree with the transient test data. The resulting model was used kind of as a virtual test bed to figure out what kind of design mods might strike the balance between these competing thermal design goals. And then we did an additional fluid model to try to quantify the potential for condensation formation. This shows the thermal desktop model. This shows the insulation around the cold plate, which has been removed on the right. The cover has been removed to show the simplified geometry that was used for the model. Tried to keep the node count down, didn't really need high geometric fidelity to get believable and useful answers. This shows the power dissipation profile. The blue line is the total power coming out of the controller. The orange line is the amount dissipated as heat in the pump. Gray line is the amount dissipated as heat in the motor. And it's based on various assumptions. We know the controller has 3.6 watts of standby efficiency, and we had to use these assumed efficiencies to calculate the heat dissipation. Measuring the electrical input to the motor was really difficult. It's a DC motor, but that's DC input to the controller board. The controller board delivers three-phase pulse width modulated power to the motor to control it, and it's extremely difficult to make direct power measurements off that kind of electrical line. For the next few graphs, I'm showing how the tuned model agrees to the test data. So I'm just going to kind of flip through them, but the dotted lines are the model, the solid lines are the test data. Okay, so with this model, we came up with a hot case and a cold case. For the cold case, we were looking at condensation formation. For the hot case, we're trying to make sure the pump and the motor don't get too hot. The analysis predicted no exterior condensation on the enclosure, but we still had to address inside the enclosure. We don't want moisture forming inside there and possibly growing mold and creating a health hazard. We found that by decreasing the thermal coupling between the motor and the pump and the cold plate, we could get things warmed up. But that also warmed things up so that the motor and the pump in particular was running a little hotter than we wanted. So an additional tweak to another thermal interface offset that and brought that temperature back down. So we found that putting the equivalent of a 20 mil G10 shim under these standoffs under the cradle and putting the equivalent of a 40 mil G10 shim under the feet for these pillars and 4 locations would get the temperatures up to where condensation shouldn't happen. And then by increasing the thermal interface between the pump and this upper cold block, we could get the pump temperature back down to within its temperature limits. In the tuned model, I had assumed that there was a 10 mil air gap in this region, and cutting that in half to a 5 mil air gap is what I actually did in the model. And with that model, we had happy pump temperatures, happy motor temperatures, and those surfaces predicted to be below 60 degrees. So that turned out to be a happy design that struck the balance between the competing thermal design goals. Unfortunately, the project decided not to modify the flight unit because it was too late. They didn't want to break configuration and open it up. And they also did a material analysis that showed we didn't have any fungus susceptible materials. The requirements permit you to have temperatures below 60 with condensation if there's no risk of fungal growth. But we still needed to look at the condensation risk because it has a potential operational effects on the motor. The motor is not designed to operate in liquid water, though it is designed to operate in high humidity. The wires are not hermetically sealed to the housing. So we still needed to know something about how much condensation could form and under what conditions. So to do that, I created a thermal desktop FlowCAD model, a very simple model. This represents the 80 cubic inch volume inside the acoustic enclosure. This represents a boundary node with a surface area average temperature taken from the model used as a boundary condition. This fluid tie connects the air in this volume to all these surfaces based on a surface area of about 350 square inches. This plenum represents the air in the rack. So we chose the most moisture-laden condition, so the warmest rack condition with the coldest cold plate condition. Turns out to be 43% relative humidity nominally. We use an extreme worst case of 75%. And this orifice represents the leak between this volume and the plenum. The leak was set up to be a phase selective leak. In other words, it would permit water vapor to pass through the leak, but it would trap liquid water inside the enclosure. This shows the average surface temperature inside the enclosure for two different conditions. The blue line represents the predicted average temperature for when the pre-cooler is operating and giving us our 10-degree Fahrenheit boost to the water temperature. And you can see that stays above the 60-degree line. So you wouldn't expect to really have a condensation issue with that, at least not in the global average sense. Could still have little spots of it because an average temperature consists of temperatures that are both above and below the average. The orange line represents a more extreme worst case where we ignore the effect of the pre-cooler, and in this case you can see temperatures get below that dew point line. So this is the boundary condition used on this node. First, I did a sensitivity check because the first thing you'd want to know is, what shape and size is the leak and is it important? I treated it as a gap times the perimeter of the cover against the insulation at the bottom. So for different gap thicknesses, I predicted how much condensation would form in the enclosure in a single condensation event. And I found out that most of the results fell on this line. Only when the gap got really small did I start to see things like this and this. And for the extreme smallest gap, I got this blue line. And even with this most extremely small gap with the blue line, I'm still reaching the steady state condensation in 3 minutes. The pump is off for 70 minutes, so the window of opportunity for forming condensation is 70 minutes long, and it's going to do whatever it's going to do in about 3 minutes. The takeaway conclusion from this is that I don't need to know the leak characteristics accurately in order to get a meaningful prediction. So didn't really spend a lot of time worrying about not knowing what the leak looked like. So here's 3 cases. I used three different analysis assumptions. They're all cold cases, all more or less worst case. We have a mild worst case, a medium worst case, and an extreme worst case. So in the mildest worst case, we don't have any condensation form. In the medium worst case, we have some condensation forming, but then it evaporates during the 10 minutes of on time. It forms again and evaporates. So it's drying itself off on each 80-minute half cycle. And in the most saturated, wet, worst case, there's more condensation formation and not enough time to get it to zero. So each time it evaporates less than is formed. And over time, you can see the curve is ramping up gently. There is a condensation accumulation. So I ran the model for 200 cycles instead of 10 cycles to see what I would get. And basically, I'm seeing the same result. And if I take this curve and extrapolate it out to a 3-year mission life, it turns out I've got about 9 grams, 9 milliliters, or a little less than 2 teaspoons of condensate formation. So even under the most extreme, damp, worst case, cold, hot, juicy ambient conditions, I still have a very small amount of condensation forming. In this case, it's drying itself each time. In this case, I'm not having any formation. I got this backwards. This is the least severe. So the blue line is hidden down here under the orange line. This is this is probably more worst case than reality. So the three conditions were a 85-degree F ambient inside the rack with 43% relative humidity. And I included the pre-cooler effect of warming the water by 10 degrees. Then we had the same rack ambient conditions, ignoring the pre-cooler effect. And then we took the same rack temperature, assumed it was 75% relative humidity, and still ignored the pre-cooler effect. In this case, no condensation. In this case, it dries itself out on each cycle. And in this case, 2 teaspoons of water after 3 years operation under these super extreme worst case conditions. So the conclusion I got from this is that condensation is unlikely to form. The risk of condensation falls between 0 and very small. Another conclusion that the project had was later during a hardware upgrade, they would take the top panel off of the acoustic enclosure and actually inspect the system to see if there's water formation inside. I don't think they're going to see any. Here's a few references. Excuse me a moment. And I want to have an acknowledgement to Warren Peters at Marshall and ES62, who created the cycle diagrams that led to the pseudo animation. I know a lot of work went into that, and I couldn't have done it. Anyway, that's it. And I guess we got time for questions.
Thank you, Dan. That was an excellent presentation.
I know I went kind of fast, but it's 60 pages and 20 minutes, so I kind of had to go fast.
Yes, I'm impressed that you made it all the way through. Honestly.
If anybody has questions later, my email is at the beginning of the presentation. I should have put it at the end.
That's good to know. I know there's a delay between the presentation and the stream at somewhere between 30 and 60 seconds. So we'll give people a chance to ask questions. In the meantime, I'll ask one. I can appreciate the conundrum of trying to shoehorn the thermal design between opposing constraints. Can you give us an idea of the sensitivity of the design options, i.e. decreasing thermal coupling at the cold plate and increasing thermal coupling at the upper cold block? In other words, how much room for error do you have to keep the design within bounds, accounting for margin and uncertainty?
Well, the margin in the analysis is only a few degrees. If you kind of think of the happy zone, where one happy zone is defined by the pump not getting too hot and the other happy zone is by things not getting too cold, the unmodified design, those regions don't overlap. With the design margins, there's an overlap with a pretty narrow margin. I've got better than average confidence in the prediction because the model was so well correlated to the test data. Nothing crazy was done to the model to achieve that agreement. Everything was done with reasonable modifications to things like heat capacity of the motor, thermal interface contacts. So as far as running a full sensitivity analysis, I guess part of that was done during the tuning process. And it was so late in the project that when I found the overlap where a happy design existed, there really wasn't enough time left to get it into the first flight unit. We will probably incorporate those changes in the second flight unit, but it is a tightrope walk, there's no doubt.
Thank you. We'll give people another minute or so to post any questions they may have in the chat.
Sure. And of course, anyone that's interested is invited to email me with follow-up questions if they like.
So you mentioned integrating some design changes into the next design, but what additional future work are you also going to be working on?
This project is winding pretty close to the end, so I'm I'm looking to get to the end of this project, and I came in probably 65% of the way through the project, and I'm relatively new at Marshall, only since 2019. So my future project is hopefully a new project where I can do things my way and not inherit a model that's had so many predecessors. But right now we're looking at doing the system testing, characterization testing, getting the system rack model tuned to the testing so it can maybe be looked at on orbit anomalies or off nominal operating scenarios. But I mean, the whole thing is geared towards trying to finish this up. I think it's supposed to be launching next summer with hardware delivery early next year. And as to how the condensation problem came to exist so late in the project, I think that had to do a lot with personnel turnover and the fact that the work was split between Marshall and Johnson. So I think some things maybe fell into some gaps. It's strictly my opinion, as I wasn't on the project when those things happened.
That does tend to happen.
Sure does.
Not seeing any questions posted in the chat. So I'd like to thank you for giving us a presentation and remind people that if they have any follow-on questions in the future, that they can contact you directly.
Well, the lack of questions is either really good or really bad. I'll try not to have my feelings hurt.
Well, there's a lot of people in the chat, so clearly they're watching. They're just
okay.
You gave an excellent presentation.
All right. Well, thank you very much. Thank you for your attention, and I appreciate it.